with the shades, man?
I like to wear them inside, Roger.
It's okay. I like to wear mine at night. But what else is going on today that you got shades for us?
Today is National Sunglass Day. And in honor of that, we'd like to talk to you guys a little bit about how sunglasses work. More specifically, how polarized sunglasses work. And before we talk about how polarized sunglasses work, let's talk a little bit about polarized light, right? Because polarized light and polarized sunglasses work together to do what they need to do, which we'll talk about in a second. So light, when it comes in from the sky, from a light source, from a flashlight, wherever, it's generally randomly polarized. It's a mix of all kinds of different light waves that are, the electric field is vibrating in all kinds of different directions.
Something like this or like this as it's coming at us, right?
Exactly.
Okay? They can be doing all sorts of different directions of their vibration.
Yeah, so it comes as a wave and it can go like this, it can be oscillating that way, or it can go this way, or it can go this way, and there's all kinds of different polarizations that kind of combine, right, to make the light we see. And so when light comes in, I've got a light right here shining on me. You can't see it, it's really bright, but when light comes from this light and it hits a surface, it reflects. But sometimes we can have surfaces like this piece of glass here where light reflects, and it also transmits, it refracts, it goes through the glass itself. But what's really interesting is at the right angle, right, light can come in and it's got all these polarizations, and when it hits this surface and makes a decision as to whether it's going to transmit, refract or reflect, light that vibrates any direction that isn't perpendicular to the surface of this glass gets absorbed, or gets transmitted, I should say. It gets transmitted, and then the light that's reflected, only the light that's polarized, that has the E field wiggling in the same direction as the surface of this glass, gets reflected.
So let me see if I got this right. So if I'm a piece of light and I'm coming in like this, I'm going to hit the glass and pass through it this direction.
Yeah, you're going to go through.
If I'm coming down like this, I'm going to hit this and scatter or come and reflect off.
Yeah, and so in some light, at different angles, even light that wiggles, this way will reflect a little bit, but there is an angle where only light that wiggles in a direction that's perpendicular to this surface, or excuse me, parallel to this surface, will reflect off of it.
Cool.
And so that's what we've got set up right here. So this light that I was talking about, light comes down, hits the glass, and only light that's vibrating in a direction that's parallel to this surface is being reflected. So we have polarized light. So polarized light means light that has an electric field that's vibrating in a fixed plane, right? So if we imagine a piece of paper and the electric field was wiggling only in the direction of the piece of paper, that light would be polarized, and that would be the polarization plane for that thing. And so we've got polarized light that's coming off of this. And so how do sunglasses work into all this? These sunglasses are polarized, and they've got Polaroids, or a Polaroid filter, you could say, where it only allows polarized light to get through. That has a polarization axis that's parallel to the axis on these lenses.
So it acts like a picket fence, like this direction, so light that is vibrating that way makes it to rise.
That's exactly right. And
Sweet.
so it's vertical, right? The polarization axis is vertical, so only light that's polarized, that's wiggling up and down, can make it, the E field's wiggling up and down, can make it through these lenses.
But you said only light that comes off of flat surfaces is going to be vibrating this way.
And that's exactly right. So when light reflects off the flat surface, its E field is wiggling this way, and these only let light through that wiggles this way. So what are we going to see if we put these on and look down at the reflection on that piece of glass?
None of the glare, I guess.
That's
None
right.
of that light.
So we're not going to see any light because these sunglasses only let light in that's polarized in this direction. And since this light that's reflected is only polarized this way, none of it makes it through. And that's the whole reason we have these polarized sunglasses, is because when you're driving, when you're out on the lake on a boat, you're generally looking down at a flat surface that's perpendicular to the axis on these glasses. And so when light reflects off of it, you don't see the glare.
Nice.
And so like fishing, you can look down at the surface of the water. When you take these off, all you see is glare. When you put them on, you can actually see into the water now suddenly.
Yeah.
And so to demonstrate what I'm talking about, let's take a little data. We've got a wireless light sensor here.
Sweet. And on my computer, I have SparkView, but if you have a phone or a mobile device that you can put that SparkView on for free, you can use a light sensor on your own, and we could determine substances, how much of that light is going to be blocked.
Yeah.
So let's give it a try. I'm just going to start. We've got a graph showing the light intensity for the whiteness of the light that's bouncing off there.
Yeah.
And I'm going to start, and you can see the sensor is measuring about 1500.
Yeah. So it sees, this sensor is pointed down at that piece of glass, and it sees the reflection of this light that you guys can't see, but there's a big studio light here. And if I look at it, it's really bright. And so if I take these sunglasses and I put them in front of that, it's only gonna measure the light that makes it through these lenses, right? But now remember, the polarization axis is vertical.
Grading like this.
Vertical. And so the light is coming off horizontal, so if I put it over like that, it'll block it. But before we do that, I want to do it like this just to show you that some light makes it through, okay? So if they're aligned like this, the light is polarized in this direction, the axis is in this direction, so it should make it through. So I'm going to cover that up.
Okay, so it went down a little bit to 900 from 1500, okay?
Right. And so now if I turn these, we should see the light
go down more.
Yeah.
And more. We're down to about 550, 650, 550.
Yeah.
About 600, sorry.
And then I'll go back.
Okay.
Right? And you see the light come back. And
yep.
If I keep going the other way, you see it goes back down.
The grate then turns all the way back over again.
Yeah.
Awesome.
So I'm having a hard time holding the sunglasses in the same place.
That's all right, but we can definitely see that as you get those perpendicular to the rays, they block them out.
Yeah.
Some portion of them anyway.
Right. And so if I take it away, we've got, full light. And then if I hold it in there again, we've got only light that's polarized in this direction, makes it through, so it's really dim. Right? And if I turn it this way, now we're letting that light that's reflecting off of that through, so it's a little bit higher in intensity.
So even non-polarized lights, shades, will block some light, but they block it out indiscriminately.
That's right. They use a filter that's sort of a neutral density.
You see everything darker, including the glare.
It just stops the amount of light that goes through. These do that as well as inhibit polarized light from making it through, some polarized light from making it through to your eyes.
Fantastic. Well, those are super cool. And if you're going to enjoy your day here, a National Sunglasses Day, that's a cool concept. But we still want to take it even maybe just one step further. As you're looking, you may have wondered what these are, which are also polarized lights. So they have basically a grate. We've pulled the molecules so they're in line like this, and they're allowing lights coming through this direction. We put a different solution in here, and just watch what happens to that solution. I've got a light behind there. As I turn this, you may notice something crazy start to happen. Right. You're noticing maybe that it's changing colors. The background gets light and dark because at this time I can see that there is light coming all the way through. If I turn if you're looking at the side of the screen, it goes dark because we've taken the screen like this and turned it. What the heck is happening to this solution? The solution is cool because it's just sugar solution. It's actually Karo syrup. And it will not only take light and block it, but it'll start to turn the way that vibrates, okay? It's a polarizing sort of substance, and it will change the way light is wiggling slowly to different directions. And it does it differently. Sometimes it'll move red a little more, sometimes it'll move green a little more, and when you turn this cross polarizer, it blocks out the other light that is now moved so much that it's going to be blocked by the second lens. So what you're getting is sometimes the red is blocked out, sometimes the green is blocked out, sometimes the orange is blocked out, and it ends up saying, oh yeah, any time some of the different colors of light is making it through, which is a great example of another phenomenon that you won't probably see that often, but you could do with your sunglasses. So we've set you up for Sunglasses Day with all sorts of cool activities. If you've got some machinery like our probes that you can determine how much light is making it through, you can measure them. If not, go out in the outdoors and find out with your pair of sunglasses or even two pairs of sunglasses what other sources of light are polarized. Check your car, look at a stream, look at the clouds, take a look at anything and see what other kinds of light. You'd be surprised to find out the amount of polarized light that we deal with.